another tube. This one is a cool Native American style flute. If you're interested in these things, there's a YouTube channel out there called Blue Bear Flutes that'll show you how to make your own Native American style flute. Pretty cool. Pretty easy too. Well, hello YouTubers. Sam Moore here again, one more time, and we're continuing our exploration. Now I know some of you have been following along this and you think, well, this guy's going very slowly. Well, there's a reason this guy's going very slowly. It's because I want to build a foundation. Anytime you see a building, you have a foundation, and that holds the entire building up. So I'm trying to establish a common foundation for everybody's understanding so that when we get to some of the trickier parts, we'll all have a good grounding to continue on. Okay, we're going to do a few minutes of review. This will be a very short one this week because it is Thanksgiving week, and basically I kind of like to eat. Okay, so far we've talked about voltage. That's the pressure, the force that moves the electrons, moves the current. We've talked about current. That's the actual movement of the electrons through the material, through the electrical material. We've talked about resistance, and resistance is the force that holds the electrons back or limits how fast they can flow or how fast they can move through there. We talked about the characteristics or some of the things which affect resistance. Longer wires make for a higher resistance. Shorter wires make for a lower resistance. Longer wires, higher resistance. Shorter wires, lower resistance. Cross-sectional area, or the diameter of the wires. Big fat wires, low resistance. Little skinny wires, high resistance. And we talked about how the wires in the pickup on your electric guitar will actually have an effect on the sound of that that pickup, and the resistance is one of the characteristics that makes that affects that sound. More turns means a longer wire, higher resistance. Fewer turns, shorter wire, lower resistance. We talked about the materials of the wire. Copper is a good wire, nice pure copper. Brass, which looks kind of like copper, you know, it's kind of copper colored, a little more yellow. No, it's not a good conductor for our purposes. For some things, it's a great conductor. They make a lot of screws and connections in electrical devices made out of brass. But you think about it, a screw's a little short thing. What's that? Short thing? Low resistance. Yeah, my nose is running. Okay. Now we're going to go a little further. We're going to talk about voltage division. Voltage division. My favorite pair off there. Okay, if I have a big long resistor, I don't know if you can see that or not. Bad lighting. Let me get a different pencil here. Now we got a new pencil. Okay, let's have a big old long resistor here. This is the symbol for a resistor in an electrical circuit. It's kind of an ugly one, but it is. Let's put a voltage across our resistor. What the heck? Now I've got a voltage across a resistor. Now this voltage is going to appear across that resistor. Heck, it's tied to it with a wire. So whatever voltage shows up here is also going to show up on our resistor over here. Okay. Now, if we have this much voltage here, say 10 volts, then we've got 10 volts here. But that's 10 volts across the whole mess. Wonder how much voltage we have across, say, half the resistor. Half the resistor. Turns out we've got half the voltage across there. we've got 5 volts, or half of 10. Wonder how much we have across 1/4 of the resistor. Turns out we have 1/4 of the voltage. In other words, this voltage divides pretty much evenly along the length of this resistor. If we've got 2 resistors in a circuit, let's make these a little shorter so I can squeeze them both on here. If we've got 2 resistors in a circuit like this, R1 and R2, and we put 10 volts across there, I wonder how that voltage divides across these 2 resistors. Well, it turns out it divides in proportion or in ratio to the total resistance. Just like our other one over here, we had a total resistance. Let me get it right side up. We had a total resistance, and the voltage divided by the proportion, or how far up and down this resistor we were. The voltage here is going to divide per the proportion to the ratio of the resistance. So if we make this one, say 2 ohms, and we make this one 10 ohms, how much voltage are we going to have here? We're going to have 2 over the total resistance here is 12. 2 plus 10 is 12. So 2 over 12, or 1/6 of 10. Or 10/6, or that's 1 4/6, or 1 2/3. So that'll be 1 2/3 volts. There's a formula for that, okay? Just like everything else in electrical, there's a formula for it. It's called the voltage divider law. I'm not going to give it to you because we're going to keep math to a minimum. So, just remember that the voltage divides according or proportionally to the ratio of this resistance to the whole resistance, to the entire resistance. Well, what's that got to do with a guitar? Okay, I knew you were going to ask. You weren't going to ask? Yeah, you were. It turns out that the volume control in your guitar is built just exactly that way, with a ratio of resistances. Okay. Remember the potentiometer. This gadget. Now, it ain't hardly that big, obviously. That's a big picture in hopes that you can actually see. Okay. These 2 connections, these 2 terminals right here, are tied to these 2 terminals. And it's just a big, long resistor stuck in there. See? A big, long resistor. This terminal, or the middle terminal, it's called a wiper. Right here, the wiper, okay, is tied to this little arm right here. This little arm moves when you turn the knob, when you turn the shaft right here, and your knob is just screwed to the shaft or glued to the shaft, or sometimes they're just pressed onto the shaft, and in a guitar it's usually just pressed onto the shaft. And when you turn that knob, you're turning that shaft, which is moving this little wiper along this big long resistor here. So where our voltage is here, our voltage is applied here, okay, from our pickup is applied right across these 2 terminals. Okay, so as we move that arm around there, we're moving up and down. You think I'd been a little more organized. We're moving up and down this resistor. So the voltage we see on this wire is going to depend on exactly where we move up and down that resistor, okay, which is tied to the voltage, which is tied to your volume knob. Pretty simple, pretty straightforward, but turn the volume knob, you're moving up and down, and you're going to see more and 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 more of the total voltage, and less 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 of the total voltage. Now, why do you want to be able to adjust the volume? Because you can overdrive your amplifier. If you overdrive your amplifier, if you put too much input voltage on your amplifier, it's going to sound like donkey snot. I don't care. It's just going to sound like donkey snot. I don't care who you are. There ain't no magic to it. Overdrive an amplifier, it's going to sound like donkey snot. Now then, potentiometers can develop problems, okay? That wiper that's in there, that's sliding around inside over that resistor that's inside this little can get dirt under it, okay? Good idea to get rid of that dirt. How can you? Well, there's two ways. One way, and probably the easiest way, is to get some cleaner, some electrical contact cleaner, spray it right there. It'll find its way inside there. That's not the best way, but it is the easiest way. The best way is actually right back here where these wires go in. You'll find there's an opening back there, a big old hole where these three wires actually go through the case, and just squirt the cleaner in there. Of course, you got to take your guitar apart to get to that, so a lot of times it's just easier to squirt it through there. Spray that crap in there, swing it back and forth, back and forth. Don't use WD-40. Go to the handy dandy store. Lowe's has it, Home Depot has it, everybody has it, has real live electrical contact cleaner or electrical control cleaner. It looks like this, okay. This can, which is a pretty big can, I think it costs like $7. It'll last you forever because you just need a few seconds. Just that's enough. Just spray it in there, turn the control a few times, and it'll clean that crud right off or right out of your controls. This is just the brand I happened to pick up, mostly because it was the cheapest one I found. CRC, QD, contact cleaner, and a bunch of Spanish stuff in here that I don't read. Quick drying, leaves no residue. Plastic safe, so it's not going to affect your pick guard. Pretty good stuff. Okay, now let's talk about where we're going from here. Next week we're going to talk about AC, alternating current. Well, why are we doing that? Well, because that's what we're feeding our speakers. That's what shakes the speakers, and the speakers are what makes the sound. So we're going to talk a little bit about AC. We have to talk about AC before we talk about the tone circuits, before they make sense. When we talk about AC, we're going to talk about the amplitude of an AC signal. We're going to talk about the frequency of an AC signal. We're going to talk about what it looks like. We may have time next week. I don't know for sure, but we may have time to get into some Fourier analysis, which is a fancy way of saying, "Huh? I didn't know that. That's some weird stuff there." But basically, we're leaning toward tone, and we have to look at Fourier analysis before we get into tone. And it would be helpful if we understood tone before we looked at the tone circuit. So we'll do a little bit of Fourier analysis, and then either next week or the week after that, I'm going to talk about electrical simulations. I'm going to be doing a lot of electrical simulations, and I want to lay some groundwork there. So things are getting excited. Hold on.